Plastic is a synthetic organic polymer made from petroleum that is suited for a wide variety of applications. Over 300 million tons of plastics are produced every year, and half of which is used to create single-use items that are meant to be disposed right after use. Single-use plastics are most commonly used for packaging and serviceware, such as bottles, wrappers, straws, and bags. Single-use plastic are a glaring example of the problems with throwaway culture. Instead of investing in quality goods that will last, we often prioritize convenience over durability and consideration of long-term impacts. Under the influence of solar UV radiation, wind, currents, and other natural factors, plastic breaks down into small particles called microplastic or nanoplastics. The small size make them easy for marine wildlife to ingest accidentally. Heavy metals and environmental contaminants can stick to microplastic, which will bioaccumulate in the tissues of animals that ingest them. Plastic don't break down at all, they just break up. Every year, at least 14 million tons of plastic end up in the ocean, and humans ingest roughly 50,000 to 120,000 pieces of plastic. Single-use plastics are traditionally hard to recycle because they fall into the crevice of recycling machinery and therefore are often not accepted by the recycling center. More than 8.3 billion tons of plastic has been produced, but only 9% of these have actually been recycled. When exposed to light, the nanoplastics unexpectedly facilitate the oxidation of aqueous manganese ions and the formation of manganese oxide solids that can affect the fate and transport of organic contaminants in natural and engineering water systems. At our current rate of plastic production and disposal, our oceans might contain more plastic than fish in 2050. Not only are plastics petroleum-based, consuming approximately 6% of global oil today as a raw material, but their production is energy-intensive, releasing more than 390 million metric tons of carbon dioxide, equivalent to 4% of global greenhouse gas emissions. Therefore, reducing plastic production would avoid 3 to 5 gigatons of carbon dioxide emission. Researchers agree that recycling and remanufacturing plastic saves at least 30% of the carbon emissions that original processing and manufacturing produce. There are some significant statistics of plastic pollution, such as 100% of baby sea turtles have plastic in their stomachs. Also, 88% of the sea surface is polluted by plastic waste. Therefore, plastic pollution threatens ocean health, the health of marine species, food safety and quality, human health, coastal tourism, and contributes to climate change. The most visible impacts of plastic debris are the ingestion, suffocation, and entanglement of hundreds of marine species. Floating plastic also help transport invasive marine species, thereby threatening marine biodiversity and the food web. Several chemicals used in the production of plastic are known to be carcinogenic and to interfere with the body's endocrine system, causing developmental, reproductive, neurological, and immune disorders in both humans and wildlife. Moreover, plastic waste damages the aesthetic value of tourist destinations, leading to decreased income from tourism. It also generates major economic costs related to the cleaning and maintaining of the sites. If plastic waste is incinerated, it releases carbon dioxide and methane from landfills into the atmosphere, thereby increasing emissions. There is evidence, too, that plastics increase ocean acidity, which could lead to coral bleaching. So, what can be done to help the plastic crisis? Governments, research institutions, and industry need to work collaboratively to redesign products and rethink their use and disposal to reduce microplastic waste. Also, consumers and society must shift to more sustainable consumption patterns. We can help avoid single-use plastic by reused bags when shopping, cook more often, reduce takeout container, walk, bike, take a public transit to buy things in person instead of buying online shipments that are full of plastic. Also, we can avoid plastic wrap by storing leftover in reusable containers. Some researchers also came up with the possible solutions to solve this problem. A group of researchers at the University of Sydney discovered two common forms of backyard fungi can break down polypropylene plastic completely in 140 days. However, degrading through mold will also release carbons, so the best option would be to reduce plastic production. There is also another type of plastic, which is compostable plastic for organic recycling. It can be collected with bio-waste and then treated in industrial composting. Microplastics can also be cleaned from water using high-pitched down waste to focus or concentrate particles in a certain perimeter. If we utilize the possible solutions effectively, we could make a positive impact on the environment and thus come closer to solving these major problems.
Temperate forests are defined as forests with a basically continuous canopy of broadleaf trees. They occur between 25 degrees to 50 degrees latitude. They are classified into two groups, deciduous and evergreen, meaning they either retain their leaves year-round or lose them according to the seasons. Deciduous forests are found in the northern hemisphere, primarily located in the eastern United States, Canada, Europe, China, Japan, and parts of Russia, while evergreen forests are found in areas with more mild winters such as New Zealand, South America, Eastern Australia, Southern China, Korea, and Japan. There's a great amount of biodiversity within temperate forests. There are 5 separate layers of a biome, each with their own unique plants and animals. Some common animals include insects, spiders, slugs, frogs, turtles, and salamanders. In North America, birds such as hawks, cardinals, and snowy owls are found in the forests. The top layer is the forest canopy tier. This consists of maple trees, walnut trees, and birch trees. The second layer is the small tree tier or understory. This consists of plants such as dogwoods, redbuds, and shadbush. The third layer is the shrub tier, consisting of plants such as azaleas, mountain laurel, and huckleberries. The ground floor consists of bluebee lily, Indian cucumber, and wild sarsaparilla. And the final tier, the floor tier, consists of plants and animals such as lichens and mosses. Temperate forests began during the period of cooling at the start of the Cenozoic era, over 65.5 million years ago. As animals began to adapt to their changing environments, the plant and animal species that survived the most were those that resembled their tropical ancestors. Temperate forests are also very important in counteracting the effects of climate change. They are ranked 12th in Project Drawdown's Solutions to Climate Change because they are expected to reduce 22.61 gigatons of carbon dioxide by 2050. Right now, these ecosystems absorb 0.8 gigatons of carbon dioxide each year. They are known as net carbon sinks, which is anything that absorbs more carbon from the atmosphere than it releases. Carbon sinks provided by U.S. forests rose 33% from the 1990s to the 2000s as forests along the Appalachian Mountains continue to grow and improve and passive restoration occurs on abandoned farmland. The global cost and saving data of temperate forests is too variable to be determined. However, human impact on temperate forests have detrimentally affected the environment and the potential solutions to climate change. 99% of temperate forests have been altered by human activities, such as deforestation, timbering, and agricultural development. Until the late 1800s, temperate forests were the epicenter of deforestation. Rising temperatures are causing a mega disturbance, with droughts, heat waves, wildfires, and insects and pathogen outbreaks. While these forests are highly resilient, this mega disturbance pushes forests past their capacity to recover. But now, Project Drawdown considers temperate forest restoration to be a very high priority, given its impressive sequestration potential and numerous co-benefits. The total area allocated to the temperate forest restoration solution is 150 million hectares of degraded temperate forests. 84% of Ireland has an opportunity for restoration. It used to be entirely forested, but much was converted to pasture. Forests are now on the rise in temperate zones because of abandonment of cleared lands and conservation efforts. The World Resources Institute has created an interactive atlas of forest restoration opportunities. Here, you can see restoration opportunity areas across the world, including wide-scale restoration, mosaic restoration, and remote restoration. You can also see the current forms and conditions of forests all across the world. Furthermore, you can see the current forest coverage, which is very important to the ecosystems inside. You can also see the potential forest coverage for future restoration. And lastly, we can see the human pressure that we put on forests. We can see that a lot of it is concentrated in the United States, specifically where we live.
Today, our usual sources of energy are coal, oil, nuclear energy, and other fossil fuels. One of the downsides of these resources is that they're limited. After squeezing all of the resources out of our planet, one day we'll simply run out. Another downside is air pollution. This is my hometown, Almaty, covered in smog. Being one day in my town is equivalent to smoking 8 cigars a day. This is the pollution map of America. In order to extract energy from fossil fuels, we need to burn them. This process releases toxic gases and air pollutants into the atmosphere, causing various health issues such as asthma, heart attacks, stroke, and other respiratory issues. Don't we just want clear skies and good health? For that, we need to find alternative energy sources. Solar energy is one of the solutions which helps to draw down carbon in the atmosphere. This method is ranked number 10 in the Drawdown book by Paul Hawken. It reduces 24.6 gigatons of carbon, the net cost is $453.1 billion, and it saves $3.46 trillion in total. The sun continuously releases 173,000 terawatts of energy, which is 10,000 times more than the energy we use. Each hour, the sun produces enough energy to provide the entire planet for the entire year. How do solar panels work? Let's figure it out! In 1839, young Edmund Becquerel found that sun can excite electrons, allowing them to move through a material. When electrons freely flow, it creates a current. This was known as the photovoltaic effect. But his idea didn't gain much attention. In 1883, Charles Friis invented the first solar panels, in which he coated a thin layer of selenium with a very thin layer of gold. But back then, it only converted about 1% of energy into electricity. Unfortunately, Friis didn't know how solar energy was converted into electric energy until Einstein published his work on photons and received a Nobel Prize for it in 1922. In 1951, Russell All figured out how to form silicon ingots that allow p-n junctions in the solar panels. Semiconductors such as silicon can be of two types, n-type and p-type. N-type has more free electrons, while p-type has holes instead of free electrons. This is the p and n junction in a solar panel cell. The n part has negative charge and the p part has a positive charge. Light photons excite the electrons in the solar cells, causing electrons to freely move at the n part. Electrons are attracted to the positive part and flow through the wires, causing electric current. Later, electrons come back to where they came from, so the cells won't be worn out or used up. This is me with my neighbor in Kazakhstan and my best friend Zirya Otmsha. Zirya has solar panels on the roof of her house.
Hi everyone!
Hey Zirya, thank you for doing this interview today. I'm very excited to be here with you with a time difference of 11 hours. I'm actually very amazed by your solar panels and would like to ask a couple of questions.
Well, the main reason for my dad for installing the solar panels was he's interested in the new technologies, the new future, and he really recommends to keep up with the new inventions. In matter of size, our solar panels are 24 square meters and they generate a total of 3,500 watts of power. So roughly saying, my dad spent about $10,000 on the electricity solar panels and about $12,000 on the thermal solar panels. The electricity bills were reduced for about 90%.
So would you recommend others to also install solar panels in their houses?
As my dad said, he highly recommends to install solar panels as you have very reliable source of electricity, and in the past 10 years there wasn't a single day when we didn't have electricity at all, while our neighbors had some times where the electricity was completely off.
That's amazing. Thank you so much for this interview and have a nice day.
You're welcome. Goodbye.
By the way, Zirya mentioned that her solar panels costed her family $22,000 in total, but those are the prices from 10 years ago. I'm happy to tell you that the prices had drastically decreased in order to spread the use of solar panels. In the past, a watt of energy cost $70. Now, it costs 20 cents. Fun fact, there are companies that install solar panels and gift it to eligible people for free. For example, Illinois Solar for All's job is to provide those panels for those who aren't able to afford solar panels. So, in summary, what are the benefits of rooftop solar panels? They will reduce your family's electricity bills. Your electricity will be less likely to go off. And most importantly, each family's usage of non-renewable energy will dramatically decrease, reducing carbon emissions. Yes, production of solar panels also use raw materials and emit carbon. but in total, amount of carbon emissions is much more less than fossil fuel energy. Of course, there are a couple complications of this idea. Not everyone can afford the energy, but as I earlier said, over time, the panels will be more accessible. Also, the most efficient solar cells that exist today only convert 46% of solar energy into electricity. That's why scientists should keep working on it until we achieve more successes in the future. And lastly, some of the areas of our planet don't have as much sun as other areas. There are cloudy days, and being reliant on the sun is challenging sometimes. If we find an efficient system of delivering solar energy from sun-abundant places to non-sunny places, the solar panels would become one of the best alternative sources of energy. Putting solar panels in the Sahara Desert has the potential to feed the entire planet with electricity, but solar farms like this is a different topic for discussion. Thank you for your attention.
Okay, so I had nuclear power, which is number 20 on the list of effective energy sources. So first off, what is nuclear power? Nuclear power, I've kind of put it together to like 4 different things. So first off, nuclear fission. Nuclear fission is the reaction where the nucleus of the atom is split into two, releasing energy, and like that's where the atom bomb comes in, or the nuke. And so how nuclear power works: nuclear reactors fill the plants with radioactive isotope, mainly uranium, producing heat energy through the process of fission. And then, although those two things are good for obtaining energy, there's also nuclear waste involved, which is it's like the excess energy, the radioactive waste from the plants is kind of harmful to the environment. And last of all, nuclear power with climate change. So it's a very low carbon energy source. So, besides the waste, it's pretty good for the environment. So some important numbers: 16.09 gigatons of reduced CO2 is what it takes. $0.88 billion is the net cost of nuclear power, and over the time of using nuclear power, there has been over $1.7 trillion in net savings. So first off, energy created by fission. So nuclear fission is, as I said, was the process of splitting the nucleus into two smaller masses and thus creating heat energy. And you can, the products of the fission are radioactive isotopes around uranium-235. This is one of the products that is produced, but that could vary in number. And the energy by the nuclear power is used to heat water, which is in the generators of the nuclear power plant, and different power turbines to create sustainable energy. So 11% of the world's electricity comes from nuclear power, and of the total energy supply around the world, 4.8% is dedicated to nuclear power. So these are some of the first nuclear power plants like around the world. First, one of the big ones was in Switzerland in 1969. Then it came to the U.S. 1970, and 83 and 87 in Russia and Canada. So it's the history. So in the early years of atomic radiation, they were just trying to figure out the process of nuclear fission from 1895 to 1945. And in the last 6 years or so, during the time of war, they started developing weapons. And as it says, from 1939 to 45, it was developed, and the atomic bomb, which was used to end the war in the Pacific. And from 1945, it was used to harness the energy to create sustainable energy during times of crisis, energy crisis. And since 1956, it is the focus has been to evolve technologically in creating reliable nuclear power plants. So there's the atom bomb, and it goes back to the fission. So split the atom, and the energy released was harnessed into a bomb. And once that bomb released, a big mushroom cloud exploded. So nuclear weaponry was first developed during World War II, and atom bombs get their energy from fission, and then other weapons like hydrogen bombs rely on the combination of fission and fusion, which is a different process of harnessing the energy. So although there are a lot of advantages to nuclear power, there are some disadvantages as well. So three of the big disadvantages are, as I said before, nuclear waste. It's very polluting to the environment, as the mining of uranium to obtain the energy source, and then the cost to build. It takes 5 to 10 years to build a plant, and it costs a lot of money. But it's kind of evened out in the savings of the nuclear power. And here's some miscellaneous numbers. So here are the list of the nuclear power plants around the world, mainly in the North America, Europe, and the Asian Pacific coast. So in conclusion, here's some more numbers. There are 450 reactors in the world. 53 of those are new power plants under construction. It is the second largest source of low carbon electricity globally, and it achieves 398.9 gigawatts of total net energy installed. So there's the bibliography. So thanks. Hope you learned something about nuclear energy.
And today I will be teaching you about silvopasture. So what is silvopasture? Silvopasture is an agroforestry practice that integrates livestock, forage production, and trees on the same unit of land in a mutually beneficial way. How does silvopasture differ from traditional pasture? In traditional pasture, trees and livestock do not belong together, and it is believed that if animals are placed on the same piece of land with the trees, this would lead to mass deforestation. However, in silvopasture, integrating trees and pasture into a system to raise livestock and intermingling livestock and trees is the purpose. And so the whole goal of silvopasture is to add a maximum number of trees without blocking too much light, which could suppress forage growth. And trees, once again, can be planted in rows, clusters, or evenly spaced, or in a different pattern. And fast-growing species such as locust, alder, willow are popular because they offer an advantage as they can quickly grow above browse height, which allows for faster integration with grazing management. In silvopasture, it is critically important to match the specific type of animal to a specific type of land or tree, because animals can be very beneficial to silvopasture, but they can also cause a lot of harm. For example, some of the potential risks could be that cows can damage young plants and trees with their weight and excessive stalking. So therefore, a fitting landscape for cows would be older trees that are hard to break, as well as soil that doesn't erode easily. And then another rule that farmers should follow is matching the trees to the type of soil and having the trees perform multiple functions. Since carbon emissions are very damaging to the environment, we need sustainable cattle production and responsible grazing, which is what silvopasture provides. In fact, silvopasture land sequesters 5 to 10 times more carbon from the atmosphere than the land of the same size that doesn't have trees on it. So silvopasture systems can store significant amounts of carbon in both soils and tree biomass. It is no secret that livestock animals produce significant amounts of methane. However, in traditional farming practices like plowing or tilling, the carbon is exposed to the air where it combines with the oxygen to become carbon dioxide. While in silvopasture, carbon is stored and wildlife thrives using carbon. This is because silvopasture allows carbon to be captured by the plants where it is synthesized and stored as sugar inside the plant. This creates a very powerful ecosystem.
With about 25% of Earth's carbon emissions having historically been captured by Earth's forests, farms, and grasslands, silvopasture can help offer lots of area for carbon capture and storage. And overall, silvopasture allows for 31.19 gigatons of CO2 reduction. Overall, the first costs to establish a silvopastoral ecosystem are estimated to be around $1,200 per hectare. And overall, silvopastoral ecosystems would cost about 41.6 billion net cost, and they would allow to save around 700 billion net savings. And overall, that makes it extremely beneficial in terms of finances in the long run. Overall, silvopasture is ranked number 9 for efficiency in reducing carbon emissions. And here are some advantages of silvopasture. So it allows increased shade from the trees, which improves animal well-being and keeps the plants hydrated as they're protected from the heat and the wind by the trees. It also enhances production overall, including in times of drought. Silvopasture improves plant nutrition intake, which in turn increases quality and size of the trees. It also allows for a higher yield, at least 10% greater than regular pasture. Silvopasture also enhances soil fertility and moisture. It protects soil from wind and water erosion, and also it captures carbon dioxide and prevents deforestation, which makes it much more environmentally friendly. Silvopasture also increases wildlife diversity. However, silvopasture does have a couple of disadvantages, which include increased time required for agricultural management, as there's more things to account for, and there's also a lack of vacant land because a lot of land is occupied with traditional pastures. Silvopasture is also more expensive. It's about 2.5 times more expensive than traditional pastoral practices. Let's look at how likely we are to implement silvopasture in the nearest future. Currently, silvopasture is practiced on about 351 million acres of land, which is about 11% of all land available for agricultural practices. In June 2020, the House of Representatives met and recognized that agricultural emissions need to be reduced and encouraged silvopasture to be practiced. However, the progress is still slow because the USDA barely invests any money into silvopasture projects, and a lot of farmers still do believe that trees and pasture are not compatible. And in addition to that, a lot of banks do not provide loans for farmers to start practicing silvopasture. Here's my bibliography page, and thank you so much for listening to my presentation.
Net zero buildings. Information found by Grace Lombardo. So, what exactly is the concept of net zero? Net zero buildings are one that is optimally efficient and over the course of a year generate energy using clean, renewable resources in a quantity equal to or greater than the total amount of energy consumed on site, as seen by the photos slipping through on the screen. What are the benefits of making net zero buildings? Number 1, they are more resilient to disasters and blackouts. This is because it will optimize passive solar gain and shading, combining with thermal mass to stabilize temperature variations throughout disasters. Number 2, net zero buildings are designed for necessity, meaning each piece of it is chosen to optimize minimal energy usage. Building out of necessity equals reducing operation costs. This lessens the risk of the project. And most importantly, number 3, there is less energy misuse. For everything that it takes, the building gives back. This is beneficial because minimizing your energy uses reduces the demand for fossil fuels, and in turn lowers the carbon dioxide levels in the atmosphere. What actions are made to create net zero buildings? The favoring of daylight over standard lights. As seen, daylight can be collected and used throughout an entire building. There can also be window louvers and overhangs that are designed to receive sunlight in winter months and are created for the need for shade in the summer when the sun is more directly above. The engineering of these buildings has an architecture that encourages the use of stairs over energy-using elevators and escalators. Walls, windows, and ceilings have maximum insulation power, R value, in order to, once again, retain heat in the winter and maintain coolness in the summer. Electrochromic glass is used to manage heat, sun, and the difference between the produced and natural temperature outside by changing its opacity. Heat exchangers are placed strategically in order to ensure each stray calorie is put to use. Air conditioning systems are made to use natural ventilation principles from nature, such as termite mounds and below thermal mass, to create natural convection and cooling breezes.
buildings such as this exist already. The Rocky Mountain Institute Innovation Center is a net zero building on the north shore of the Roaring Fork River in Basalt, Colorado. The center focused on heating and cooling the people, not the space, to save heating and air conditioning energy. Net zero even exists in Chicago. There's a neutral Walgreens in Evanston that is the first of its kind. Now, the most important is impact. It is important to note that even though net zero buildings do exist, they're still in the works and hypothetical. Everyone has its own outcomes and solutions to energy-related issues. But if 9.7% of new buildings are net zero in 2050, then the integrated opportunity is 7.1 gigatons of carbon dioxide, giving this a number 79 ranking by Paul Hawken. Thank you, and these are my sites.
Hi, this is Jin from AP Chem Section Green, and for my final project, I will be talking about the solar farm. So these are the chapters in the Google slide. So what are solar farms? Solar farms, also known as solar power plants or solar parks, are large-scale installations that harness the power of sunlight to generate electricity. These farms consist of thousands or even millions of solar panels, which convert sunlight into electricity through the photovoltaic effect. So what is the photovoltaic effect? It can be described in 7 different steps. First, the semiconducting materials. The semiconducting materials is mostly used as silicon because for silicon's abundance, stability, and favorable electrical properties. Then, energy absorption. Energy absorbed from the sunlight through the semiconducting material, and there comes electron excitation. The energy from the absorbed photons excites the electrons in the semiconductor's atoms, causing them to break free from their atomic bonds and become free-moving. These energized electrons are now able to flow through the material. Fourth, the electric field. Solar cells are designed with a built-in electric field. This electric field exists due to a junction formed between 2 layers of the semiconductor material with different electrical properties. The most common, as shown in the picture, is the p-n junction, where one layer is doped with impurities to create an excess of positively charged particles, which is the p-type, and negatively charged particles, which is the n-type. Fifth, the electron flow. The presence of the electric field within the solar cell causes the free electrons to move toward the n-type layer, while the positively charged holes move toward the p-type layer. This separation of charges creates a voltage difference between the 2 layers. Now, the current generation. When an external circuit is connected to the solar cell, the separated charges are compelled to flow through the circuit due to the voltage difference created by the electric field. This flow of charges constitutes an electric current that can be harnessed for various applications. And last is electricity production. Multiple solar cells are interconnected to form a solar panel. When sunlight falls on a solar panel, each individual cell generates a small amount of electrical current. By connecting these cells in series or parallel configurations, the total current and voltage output can be increased to provide a useful amount of electricity for powering devices or feeding into the electrical grid. The main requirements of solar farms are land, sun energy, and solar panels. So how do solar farms bring down CO2? First, by carbon-free electricity generation. Solar energy generates electricity without emitting any carbon dioxide or other greenhouse gases, unlike fossil fuel-based power plants that burn coal. Solar farms harness the sun's energy through photovoltaic panels, as discussed before, to produce electricity without any direct CO2 emissions. By displacing electricity generation from fossil fuels, solar energy reduces CO2 emissions associated with power production. Another way that solar farms decrease the amount of CO2 in the atmosphere is by energy substitution. Energy substitution is when solar energy can replace fossil fuel-based energy sources in various sectors. Solar farms integrated in the electricity grid can supply clean electricity to homes, businesses, and industries, reducing the need for power generated from CO2-emitting fossil fuel power plants. By substituting solar energy for fossil fuel energy, we can significantly reduce CO2 emissions. The budget. The budget is around $1 million, and most of the cost is by engineering, equipment, development, and installation. So, is solar farms really realistic? Why it's realistic is the growing concern about the environmental and climate change. The urgency to address climate change and reduce greenhouse gas emissions has led to a growing global focus on renewable energy sources. Solar farms offer a clean and sustainable solution for electricity generation without contributing to carbon dioxide emissions. Thus, governments, businesses, and individuals are increasingly recognizing the need to transition to renewable energy sources, and solar farms play a significant role in achieving these sustainability goals. So how likely is solar farms to be implemented in the future? Solar farms are a highly realistic and feasible solution for generating clean and renewable energy. The technological maturity and advancement in solar photovoltaic technology have made solar farms a commercially viable option. The cost competitiveness of solar energy with declining prices of solar panels and improved manufacturing processes has made solar farms increasingly affordable and competitive with traditional power generation methods. Thus, this is why it is most likely that it will be implemented in the future. The pros and cons. The advantages of solar farms are the prices, the reduced CO2 emissions, the environmental awareness, and alternative energy. However, the disadvantages are the high initial cost of installing panels, solar energy storage being very expensive, and solar panels being very dependent on sunlight. This is a quote by Thomas Edison, which talks about how important it is to transition to a new source of energy. Thank you, and these are my sources.
Hi everyone, my name is Chandravi, and today I'll be teaching you about the mining of rare earth metals, also known as REE. What are REEs? Rare earth elements are a set of 17 elements in the middle of your periodic table. Present day, these rare elements are growing in demand due to their catalytic properties. For an element to have a catalytic property, it means that it's able to increase the speed of a chemical reaction. And these elements are not only abundant, but they're also at a low price, which is what makes them appealing. How do we mine these rare earth metals? There are two types of mining, in the sea and on land. In the sea, through the usage of hydraulic pumps and filtration, robotic machines excavate on the ocean floor and filter, which leads to these metals. On land, through open pit methods, rock is blasted open and loaded into trucks, and through separation and purifying, we are able to separate these metals. Drawdown in CO2. The current model of mining rare earth metals seeks to reduce global carbon emissions by 50% by 2050. These rare earth metals are strong magnets, which leads to higher demand. For, quote, they are critical in the construction of direct drive wind turbines and permanent magnet motors for electric vehicles. Wind turbines and electric vehicles both reduce carbon emissions, which leads to cleaner forms to produce energy, which is why these metals are so appealing. Costs. As of 2015, the net cost of mining rare earth metals is between 14.8 to 16 billion. As demand grows, prices of rare earth metals have remained stable due to cheap Chinese production. As seen in this graph over here, as we go into the 21st century, China is seen to be the largest producer of rare earth oxides compared to the USA and other countries. Pros and cons. Some challenges of mining rare earth metals is that although all these elements are abundant, each one requires different processing and extraction technology, which makes it super costly. Another environmental challenge is the fact that there is the potential of environmental and ecosystem damage. For example, acidic waste and contamination of drinking groundwater, not to also mention the disruption of ecosystems around the mining areas. Some pros of REE mining is the fact that it's renewable energy, and we can use these elements for essential items, to power these essential items such as smartphones, digital cameras, computer hard disks, televisions, computer monitors, etc. Is this realistic? The mining of rare earth metal is popular present day and is seen to be on the rise of production because of its environmental friendly effects, in addition to its wide uses, as stated before. In our future, due to this rise of demand in renewable and reusable energy, this will lead to new mines and processing plants, which will increase effects as an increase of pollution and increase in disruption of other ecosystems around mines. Thank you, and this is my bibliography.
I'm going to be teaching you guys about methane digesters. So, how does a methane digester work? To answer this, first we must find out what a methane digester is. Methane digesters, or anaerobic digesters, are devices that use anaerobic conditions to break down organic matter and produce biogas. And for those who don't know, anaerobic conditions are conditions without oxygen. The biogas that is produced during methane digestion is primarily composed of methane, along with a nutrient-rich fertilizer called digestate. The simplest methane digester would need to be an airtight container where the organic waste is mixed with water, and inside that digester, microorganisms like bacteria break down the organic matter through a series of biochemical reactions. These reactions are the same reactions that produce the biogas that is captured in the device and later utilized as a source of renewable energy. So, now for the chemistry behind methane digesters. Firstly, we have hydrolysis, then fermentation, then acidogenesis, and then acetogenesis. In order for organic waste to be converted into methane, multiple chemical reactions must take place in an anaerobic environment. These reactions listed all build up the needed compounds to carry out the most important reaction, methanogenesis. Two methanogenesis reactions happen inside methane digesters. One where the acetic acid produced during acetogenesis is decomposed into methane and carbon dioxide, and the other where the dihydrogen produced from acetogenesis is combined with the carbon dioxide produced in the previous step to create water and methane. How do methane digesters help draw down the CO2 in the atmosphere? When methane is released to the atmosphere, it eventually oxidizes and breaks down into carbon dioxide through natural processes. So the use of methane digesters helps capture that methane and effectively uses it before it escapes to the atmosphere and decomposes. It is estimated that by 2050, large methane digesters would have reduced 8.4 gigatons of CO2, and small ones could reduce a little under 2 gigatons of CO2. The financial impact. Simple methane digesters that are used on farms or in houses can vary in cost from thousands to tens of thousands of dollars. Large complex digesters for large corporations or schools could have million or billion-dollar designs. However, installing a methane digester would be a worthy investment, as the produced biogas could be used to both power and heat that property that the digester is located on. It is estimated that by 2050, the investment in the use of large methane digesters would have been a little more than $200 billion and would have saved us almost $150 billion, and that the investment in small methane digesters would have approximately been $15 million, saving us almost $14 million. How realistic is the adaptation of methane digesters? The adaptation of methane digesters is very plausible. They have a very simple design and are a viable solution for addressing renewable energy production, waste management, and greenhouse gas emissions reduction. They are ranked 30th and 64th in the most effective environment-preserving devices, while being just as costly as solar panels. I believe that the implementation of these devices in our everyday life would see its full potential to contribute to a more sustainable and circular future. Accompanied by people's growing awareness of their ecological footprint, the installment of methane digesters in homes could help reduce families' ecological footprint size. Now, how likely is it that we'll be implementing methane digesters in the near future? Hopefully, it's very likely that there will be a larger implementation of methane digesters. Popularity among devices is growing partially because the growing awareness of climate change. Methane digesters are now fairly common on farms, and it is rapidly spreading in the homes of foreign countries. Using some wishful thinking, I predict that we will all know methane digesters very well within the next few years. Finally, what are the advantages and disadvantages of methane digesters? So to answer this, I made a pros and cons list. Pros are, it lowers the greenhouse gas emissions, creates a nutrient-rich fertilizer, it creates renewable energy, sustainable waste management, and it also creates a new profession surrounding methane digesters. The cons is that it does have a large initial investment, and that it does require energy to power the device.
All over the world, from San Francisco to Germany to Seattle and to Singapore, green roofs have been on the rise. I've noticed that many cities, from the eagle-eye view, appear as endless blotches of gray and brown. That's because the building's priority is to protect inhabitants from the elements by withstanding the sun's harsh rays or being able to take a beating from hail. As what was once natural land area is concealed by a dense population of buildings and pavement that retain heat, concrete cities have led to the emergence of the urban heat island effect, where cities are considerably warmer than its rural neighbors. Green roofs are a way to combat this dilemma. As cities are not going to stop growing, it is important to be conscious of ways to avoid its harmful repercussions. In rural and suburban areas, plants engage in a process called transpiration, where it absorbs water from the ground and acts as a natural air conditioner. Because in a city, the pavement and buildings absorb light energy due to their darker color, temperatures are higher. Even if a 7 degrees Fahrenheit increase doesn't seem much, this can cause dehydration and heat exhaustion, and power outages from needing more energy to operate air conditioning. As companies typically source energy from fossil fuel power plants, rising demand for electricity leads to more air pollution and greenhouse gas emissions. Beyond health concerns that disproportionately target older adults and younger children, pollutants can exacerbate smog, acid rain, stormwater runoff that contaminate water resources and aquatic life, and CO2 emissions that worsen climate change.
Green roofs offer a direct resolution to the issue of heat islands, as the vegetation is able to offer some well-needed shade and reduce temperatures up to 30 to 40 degrees lower than the conventional rooftop. Constructed from a growing medium, soil in this case, plants, and a waterproofing membrane meant to restrict the flow of water through a surface, green roofs are formed overlaying a traditional roof. When implemented, it can offer a multitude of environmental, social, economic, and aesthetic benefits. Alongside lowering temperatures, green roofs also reduce energy use, as there is less need to rely on outside heating and cooling sources. And green roofs also help manage stormwater runoff, which is critical to preventing water contamination. And also, this contributes to quality of life, because not only is it pleasing to the eye, but it encourages biodiversity and helps create a relaxing green space for human interaction, which benefits productivity and lowers blood pressure. One particular benefit of green roofs is that it helps draw down CO2 emissions, as the vegetation levels act as living insulation, while the soil and biomass can capture carbon. The floor right below the roof can see up to a 50% drop in energy use for cooling, as green roofs help moderate temperatures year-round. Because of this, both cost and greenhouse gas emissions are lower with energy required for heating and cooling. And despite the fact that upfront costs for green roofs are higher than traditional ones, green roofs have double the lifespan. More specifically, it has $1.39 trillion in net cost and $988.5 billion in net savings. And green roofs are typically more expensive than traditional roofs, and also have pretty costly maintenance on top of that in terms of fertilization, irrigation, weeding, and more. However, to offset this cost, there are longer-term savings to be considered, from decreased energy spendings and the durability of a green roof. Cities like New York City also offer tax rebates, such as a $5.23 return for each square foot and up to $15 in priority community centers. Ultimately, over a 50-year time span, green roofs return anywhere from $2 to $14 more than traditional roofs, though it depends on the complexity of said green roof. But despite all that, higher costs through materials and labor and maintenance remain two big limitations that prevent us from seeing green roofs everywhere. Another disadvantage is that green roofs are prone to leaks. When you water the plant and vegetation, inevitably leaks are going to come through, and it's difficult to pinpoint the problem with so much organic material. Ultimately, the future of green roofs appears pretty bright, especially as countries and governments are offering construction incentives for green roofs and building policy, and also mandates like in the US, 15 to 30% of roof space on new buildings must be green, use solar powers, or both.